Bismillah ar-Rahman ar-Rahim. Welcome to Chapter 4 of EEE 223 Industrial Control. As we have discussed previously, we have four controllers: proportional controller, integral controller, and derivative controller. Also, we have discussed how to combine one or two controllers together, like a BI controller or PD controllers. In this lesson, we're gonna discuss the most commonly used controller worldwide. You can say it is the PID controller. PID is proportional integral derivative, and as you remember that the output of the controller in this case we call it MPID equals to the output of the controller for the proportional plus the output of the controller for the integral and the output of the controller in case of the derivative controller. So if we combine them, we're gonna get this equation, and you should remember this equation. It is very important, and as you can recall, this is the proportional part, and this is the integral part, and this is the derivative, while MR is the bias. The bias here is when the error is zero, so this part or the change in the error will be zero, this part will be zero, and then this part also will be zero, and this part will be zero. Then the MR will be equal to the M, which is the controller output. So this is just one case that we should look for it. So this is very important to know. Again, here we have the gain KC, the gain TI, the integral time, and TD is the derivative time. This graph here is for BI, the controller response, and we have three parameters: the proportional gain, integral gain, and the KD, which is the gain of the derivative. In this case, in this figure, we have different gains. However, in our PID equation, we have the same gain KC. So just to explain to you that every part, if we change the gain, we're gonna change the whole controller part, either P or I or D. So here KP is for the gain for proportional, KI for the gain for integral, KD is the gain for the derivative. So if we have changed the gain for the proportional only, so we'll have more overshoot for the process, and we're gonna have the offset here. So in case if we make this one 3, in case we have changed the I, for example, to 5, then we will have more overshoot, higher overshoot, more oscillation, and it will take a long time to reach to the steady state or to come closer, and it will eliminate the offset, as you know. For the derivative, normally the gain is very small, so like 0.3, 0.2 or something like that. So normally the response will be fast, and the oscillation will be less. There is no overshoot, and it should reach to the set point. The process variable should reach to the set point within the minimum settling time. So this will give you the overview of how these two or three controllers can be combined and what's their effect or impact on the output of the controller and the process variable at the end. So this is make it clear that we need what we call tuning. Tuning is the adjustment of these parameters, the the gain of the proportional, the time of the derivative, and the also the time for the an important topic in this chapter is the tuning of the parameters of the proportional, integral, and derivative parameters. So the tuning here is very important because you're gonna change these parameters in order to maintain the process variable within acceptable variation. For example, the overshoot percentage, the settling time, and also the offset or the error offset. So these are, or the dead time also. So these are parameters. So the operators, maybe they are not happy with the variation or the performance of the process. So they ask you to do the tuning. This is very important while you are doing, inshallah, your engineering, or you'll be an engineer, inshallah, or technician. So this is one of the most important technique in the control scope. There are two types of tuning. One is the closed loops tuning, the other one is the open loop. The closed loop is when the control or the feedback loop system, which is the closed loop system, is complete. So the process variable or the controller will continue to do the difference between the set point and process variable, and act or generate an output to the final control element. While in the open loop system or open loop tuning, so the controller can be switched to the manual mode, and there is no feedback in the system. And this is more risky here. There is a risk. So the operator should always monitor and maintain the process variable within limits. Before we go to the tuning procedure, we have the quarter decay ratio. The quarter decay ratio is when the performance of the process variable in this form. So here we have this peak and this peak. This is B and A. So A wave is quarter with respect to B. So if we are dividing from here, we have to find how much is this one here. So B over A equals to 1/4. So if B equal to 1, A should be equals to a quarter. This is what we call it quarter decay ratio wave form. Okay, this is very important. You're gonna see it in the next slide. So here first we're gonna do the closed loop tuning. Previously, if you can go back also to this one, the closed loop tuning and open loop tuning. This is generated or established by Ziegler and Nichols. They are American engineers. In 1942 they have developed these two methods. So these are names of the after those scholars. So this procedure is very important for the closed loop tuning. The step one is to find the ultimate gain, KCU, and ultimate period, which is PU. The ultimate gain is the gain of the proportional controller, at which the loop oscillates with constant amplitude, and while the ultimate period is the period of the resulting sustained oscillation. The ultimate period, it's the time in time, or the gain also either in percentage or it's absolute. So if we have this sustained oscillation, as you see here, these are sustained oscillation. They are equal. They are the same oscillation. From here to here, from peak to peak, we call it PU. Okay, this is the ultimate period. Okay, so this is happen when Kc equal to Kcu. When the gain is equal to the ultimate gain, we have to stop and find the period, ultimate period, from peak to peak or from valley to valley. Okay, so this is the same thing. When the control gain is less than the ultimate gain, as shown in figure B here, then the process variable or the process performance will be oscillating like this. However, if the control gain is greater than the ultimate gain, so the performance of the process variable will oscillate and will be greater and greater. So this is, we don't want to have this one and we don't want to have this one. So this is the figure 1, which oscillates the performance, or the BV oscillates like in cycles and continuously, and it has the same peak and with the same period. This is what we call it, where we can find the ultimate gain and the ultimate period. Now, after we have find the ultimate gain and ultimate period, we have to follow these steps in order to determine the ultimate gain and ultimate period. These are the steps that we should follow in order to find the ultimate gain and the ultimate period, and then we have to apply the Ziegler-Nichols table. So first is to remove the integral mode. Removing the integral mode is by putting the integral time to the maximum or set the integral mode to be off. This is very important. So if you go back to the integral mode equation, and you will find if we put the integral time to the maximum, then we will decrease the effect of the integral controller, or we can put it simply off. Second is to remove the derivative mode by keeping the derivative time to its lowest. So if we make it to make the derivative time to the lowest value, then we can eliminate the effect or the impact of the derivative mode, or we can set it to 0. 3 is set the control gain Kc at low value and put the controller in auto mode. So we have to select or set the controller gain to the lower value and put the controller in auto mode. 5, we have to increase the gain in small steps, gradually until sustained oscillation, like what we have seen before. So until we have got the sustained oscillation after small set point change or load change. When the amplitude of oscillation remains constant, the ultimate gain has been reached. So that's why if you go back to this until we reach such graph, so we'll have continuous oscillation with constant peak and constant time. So we can find the ultimate gain. And then we have finally measure the period from oscillation and record it as ultimate period. So the output of the controller will be the output of the proportional plus the output of the integral plus the output of the derivative. So this is for PID, and this is the equation. So if we have again, this is the proportional gain, and if we increase the time here to the maximum of the integral, then almost this one will be 0 or will be cancelled. And then to eliminate the derivative, we have to make TD to the lowest or make it 0. So this will be 0. Okay, so this will be left with only one gain here. Step 2, when we find the ultimate gain and ultimate period, we use Ziegler-Nichols tuning table. This table is very, very important. You can find it anywhere, you know, especially in the process, chemical process or process reaction in order to do the PID. So this is very important table, and inshallah, if you're going to be engineer, you'll see how to use this important parameters and how to obtain the right parameters in order to achieve optimal process performance. So after obtaining the ultimate gain plus the ultimate period, we need to apply Ziegler-Nichols tuning table that we can tune our controllers for quarter decay ratio response. So this is we should, after implementing this, we should get the quarter decay ratio waveform. The Ziegler-Nichols tuning table, this is for the closed loop. So if we are using only proportional, then we have to multiply 0.5 by the ultimate gain. However, so this is the gain here, and this is the reset time, the integral time, this is the derivative time. If we are planning to use the PI, so we have to multiply 0.45 multiply the ultimate gain, while to find the integral time we have to divide the ultimate period, we divide it by 1.2, while PID, in case of we are using the PID, then we have to find multiply 0.6 by the ultimate gain, and to find the ultimate find the reset time or the integral time, we have to divide the ultimate period by 2, and the derivative must be divided by 8. And again, this is for closed loop method. Just to notice that in case of we are dealing with B or P proportional and PI and PID. So here we can see that here is 0.5 multiply KCU, but here we multiplied by 0.6 because we have the derivative. We have added the derivative here, so the derivative is, you know, it will speed up and accelerate the process variable performance. So we can add, you know, higher gain here. So the derivative will make the performance faster. So we can increase the gain in this mode. After implementing the new calculated values of Kc, Ti, and Td, the quarter decay ratio response is shown here. So for I is the disturbance. So if you made the disturbance, then we can see the part here is, you know, still it's showing, you know, some, you know, oscillation, but we would reach the set points immediately after the second wave. So here still it's quarter decay, means that A equals to you know, or P equal to A over 4. It's almost the same thing, but we can see the change of here the set point and a little of disturbances here in the when it reaches the set point, the new set point. Here we have an example of the PID tuning. Here 4.1, determine the QDR quarter decay ratio tuning parameters for a PI and PID controller. If the controller gain required to cause sustained oscillation, this is very important, sustained oscillation is 0.9 and the period of oscillation is 4 minutes. So what do you mean by sustained oscillation? Is the continuous oscillation where we can find the ultimate gain and the ultimate period. So if we assume that we have this oscillation, assume it that's equal, so we have the gain here and the gain is KCU is equal to 0.9, while the period PU means from this point to this one to this point, PU is 4 minutes. So we use the table, Ziegler-Nichols table, to find P is you multiply 0.5 by the KCU, which is 0.9, so is equal to 0.45. For the PI controller, we have to multiply 0.45 multiply the ultimate gain, which is it's going to be 0.405, while ultimate period over 1.2 will give us the reset time. So here we'll have the 4 over 1.2, which is equal to 3.33. Okay, for the BID we have 0.6 multiply KCU, which is going to be 0.54. Here we have PU, which is 4 divided by 2, which is 2. And finally, PU over 8 in order to find the derivative time, which is going to be 1 over 2. So this is a clear and direct example with the given gain, ultimate gain, and ultimate period. In this example, 4.2, control gain for this oscillation is 2. Determine the QDR tuning parameter for a PI and PID controller. So I give you the process performance here. So we have this from peak to peak. So we have from peak to peak, which is PU. So KCU, the ultimate gain, equal to 2. So here, as you see, we can see from this graph that this is a sustained oscillation. Means this is what we need, and we can find the optimal gain and the optimal period. So KCU equals to 2, while from graph we can see that from this point to this point how much time we can we can calculate here. So 20 minus 10 equals to 10 what? Minutes. So PU, which is the ultimate period, equals to 10 minutes. So directly, if we have the ultimate gain and the ultimate period, so this is the gain, we can use them and find the parameters of PI and PID using the Ziegler and Nichols table. So this is very important technique, and every student should make sure that he understands how to find the ultimate gain, the ultimate period, and how to calculate the parameters using the Ziegler and Nichols table.